Okay, so we just finished lab techniques and lab safety. Now we're going to actually get into chapter 1 of the textbook. Those techniques, safety, that isn't in the textbook, but anything from here on out in this course will be in the textbook. So if you want to follow along, you can start reading chapter 1. So the first question is, what is chemistry? Well, chemistry is the study of matter and the changes that that matter undergoes. And it's central to all the sciences. It's called the central science for a reason. Everything around us that we see, feel, touch is made of matter. So chemistry applies to really anything you can think of that deals with all the stuff around us. Um, and if you think about the other sciences, if you look at biology, you deal with life. Uh, all our bodies are made of matter. That matter follows the rules of chemistry. So if the further you go into biology, you'll end up breaking down living processes at a deeper, deeper level, and eventually you get to atoms and molecules interacting, and you got to know the chemistry of how they're doing that. Um, or if you work with geology, with rocks, you need to know how rocks degrade, break down, and what chemicals they react with to dissolve. All that involves chemistry. So chemistry is very very important to a lot of the different sciences. If you get into any science, you're going to know at least a base amount of chemistry. Hold on, my slide isn't clicking. There we go. So basic versus applied science. Excuse me. So basic science is just trying to find new information just because we're curious. So you can read the definition here. Advancement of scientific knowledge and understanding, basically for the sake of just knowing something new. So if I want to know how many stars are in the universe, I'd start by taking a telescope, pointing at the sky, picturing it, trying to see how many stars I can see. Does it really help anyone? Does it solve any problems here on Earth? Not necessarily, no, but we're curious creatures. We like to know that stuff. So that would be basic science. Now, if I have a problem and I apply all the science that I know to try to solve that problem, that would be called applied science. It's focusing on solving real world problems. So one example is making products. If I want to know how to make a better fuel for my car that's more efficient, it gets me more power, I would apply chemistry to that to try to make a fuel that burns maybe hotter, faster, cleaner, so that my car is more powerful, fuel efficient, goes further, things like that. Now, one thing I want to point out is that sometimes basic science will turn into applied science. What I mean by that is maybe I'm just looking at different compounds and seeing how they behave, and I find out that one of them is really, really useful for something. Just let's say I'm working with petroleum products, oils and fuels, and I find out that one fuel happens to burn really clean. Well, I might take that and say, okay, I'm going to apply that fuel and try to tweak it and modify it now because I see that there's a need uh, for that product. So sometimes basic science will eventually turn into applied science. Things that we just wanted to know about eventually become useful, and then they turn into applied science. The last one here is technology is just the practical use of scientific information. So the example there is your smartphone in your pocket, assuming you have one. It's taken a lot of technology, a lot of basic science, and a lot of applied science to make that product. Okay, so matter and its properties. Mass is the amount of matter measured in grams. Mass is anything that has mass. Matter is anything that has mass and takes up space. So mass is different than weight. Weight is the amount of gravity, or is the force of gravity pulling down on something. Mass is just how much stuff is it made of. And we'll talk about the difference between mass and matter, I believe, in chapter 2, or between mass and weight, excuse me. An atom is the smallest unit of element that maintains its chemical identity. The next slide will explain that better. So take that definition, have it in front of you. Here's the example of this. I have a pencil. Now I have pencil lead here. It's not actually made out of lead. It's actually made out of graphite. Now graphite is pure carbon. Carbon is an element. Now, sorry, which element is it made out of? I answered that question for you already. If I were to zoom in on this graphite here, This is what it looks like at a molecular level. You can see that there's sheets of carbon. You see that they're combined in a honeycomb pattern, but you can see that there's layers here, especially when you're looking straight onto it. That's actually why the layers scrape off so nicely onto your paper. You're actually scraping individual layers off, or multiple layers as you go. Now, this is a compound, a big compound. If I were to zoom in on one tiny little atom here, this is an atom of carbon. Now, this carbon atom behaves exactly like all these carbon atoms, because it's still carbon. But this carbon atom, if I take this pencil and I divide it in half again and again and again, eventually I'll get down to the molecular level. Then I'll get down to the single atom level. This carbon atom is still carbon. It hasn't changed. Nothing's changed from here to here. We've just went from having a lot of them to one of them. But if I were to break this, carbon atom in half, whoops, I missed that completely. If I were to break it in half, it's no longer carbon. So this carbon atom is the smallest piece of carbon that I can have and still be able to call it carbon, and it still has the properties of carbon. But if I were to break this up, it's no longer carbon. So an atom is the smallest piece of an element that still retains its properties. So you got the little note there. Now elements. So elements are considered a pure substance. They can't be decomposed by ordinary chemical means, and they're made up of one type of atom, just like that graphite was. It was made up of just carbon. It was a pure substance, carbon and only carbon. It's found on the periodic table, and there's 118 known elements. 90 are naturally occurring. The others are made synthetically in a lab. You're not going to find them in nature. Now, a trick to finding them on the periodic table, or to know if something's an element. If something ends in ium, I-U-M, it's probably an element. So if you think of all the elements that end in ium, like lithium, helium, if it ends in I-U-M, it's probably an element. That's just a little hint to help you find elements quickly. Now, not all elements end in ium. If you look here, we got iron on this periodic table. Doesn't end in ium, but a lot of elements do. So if you see ium, you should be thinking element. Compounds. When elements combine, they form compounds. Compounds are also pure substances. They can be broken down by chemical means, but they're still pure. Now, what you'll see them written as a chemical formula or as a name. So like NaCl is the formula, sodium chloride is the name. And it contains a chemical bond, which we get into bonding more in later chapters. They're the same everywhere. They're uniform composition. That means that no matter if you have a glass of water and it's pure water, no matter where you look in that glass of water, it will look the same. There's not chunks of other things or anything like that. It looks the same everywhere. Another way to know if you have a compound or not, did we use it in lab? If we used it in lab, it's probably a compound. So things like baking soda, salt, vinegar, those are compounds if you remember using them in lab. And here's some more examples. Hydrochloric acid is baking soda. I got that. Salt, water, there you go. Some hints to know if it's a compound, and sorry I already wrote over there. If you see ate, or ide, it's probably a compound. Kind of like ium tells you it's an element. Those three endings usually indicate that it's a compound. Okay, now mixture. The last two things, the elements and compounds, were pure substances. Now we're going to start talking about mixtures. There's two types of matter. There's mixtures or pure substances. We already talked about the pure substances. Now mixtures, when you combine two or more substances, but they have to retain their own property. So what I mean by that is if I mix sand and salt, they don't chemically combine to form a unique new substance. The sand and salt, let's say I put them in a beaker, you can still see the sand and the salt. They each retain their own unique properties that they had before you mixed them. They don't change. They're just together now. So there's no chemical bond between the substance, and the composition can vary. If you have a sand and salt mixture, it could be a little saltier on top, a little sandier on bottom. It's not uniform throughout the whole sample. Now, the original properties remain even after the mixture is separated. So if I were to separate the sand and salt, they're still sand and salt. Before I mixed them, while I mixed them, and after I separated them, they always retain their original properties and their identity. And then most substances are mixtures in nature. Sorry, you can always pause if you need to write this down. I just try to get these videos done quicker. So a summary, we've got matter. Now, matter can be classified as a mixture or as a pure substance. Now, of the pure substances we talked about, you should know this, elements and compounds. Of the mixtures, we can break mixtures into two categories, which we haven't yet, so that'll be next. Heterogeneous or homogeneous mixtures, and we'll talk about those now. So this just kind of summarizes what we've done. You got matter, can either be pure or a mixture. Pure substances are elements and compounds, and these are your two types of mixtures. Now, a heterogeneous mixture. The composition and properties are not uniform, so there's different phases or parts present. So example, granite, clam chowder, or pizza. So what we mean by not uniform, if I look at this granite, I can clearly see different parts of this granite. There's the dark parts, the light parts. Same thing with this pepperoni pizza. There's pepperoni, cheese crust. It's not a uniform mixture. I can clearly see different parts. Same thing with the chocolate chips and the ice cream here. Now that differs from a homogeneous mixture where the composition and properties are uniform. Now this sounds kind of like a pure substance, but it's not. So something's mixed, but it mixes uniformly. So a solution or alloy, so a solution is a solid dissolved in a liquid. An alloy is a mixture of solids, like a solution of solids. And make sure you know your alloys. You got bronze, brass, I'm trying to think, steel, those are common alloys. If you come across those on the test, you need to know that they are a homogeneous mixture. So we got salt water, liquid soap, brass. So at brass, I added bronze to that list. I think I added steel. I'm trying to think of anything else. Bronze, brass, steel, any other alloys. I'll come up with them in class if you can think of them. Bring them to class and tell us. Salt water is an example. Salt water, we know that it's a mixture of salt and water, but if you look at a glass of salt water, it looks uniform. It looks like a glass of water. So that's why we call it homogeneous. Homo means same, hetero means different. So if it looks the same everywhere, it's a homogeneous mixture. Vanilla ice cream looks the same everywhere. Now, we're going to add one more rule here, the eye test. If it looks the same everywhere and you know it's a mixture, we're going to call it homogeneous. If it's a mixture and it has different parts, we're going to call it heterogeneous. The reason I bring this up is because milk, looking at it, looks homogeneous, but technically it isn't. If you look at it under a microscope, there's solid fat particles floating around. So there technically is different phases present, but for this class, we are going to call this a homogeneous mixture. Because if I look at it, it looks uniform. We'll just make it simple. Same thing with blood. If you look at it under a microscope, you'll actually see solid little particles in there that would make it heterogeneous. But if you look at it with just your eyes, we're going to call it homogeneous. Chicken noodle soup, that one's obviously heterogeneous because it's definitely a mixture and there's definitely different chunks in there and different parts. Now this is a tricky one. Soda or pop, it looks uniform throughout, but technically there's two phases present. You got the liquid, which is made of a mixture of sugars, different flavors, and water, but there's technically a second phase, and that second phase is the gas bubbles that you see here. So this would be a heterogeneous mixture. Okay, here's how you tell if something is heterogeneous or homogeneous, and I'm running out of time because I want to keep these to 15 minutes. So I will write this down, and we can always cover this in class if you have any questions about it.